Okay, 30 done. So to 31. That rhymed. 31 like this. Okay. The ball starts falling with zero initial velocity on a smooth inclined plane, forming an angle alpha with the horizontal. Having fall distance h, the ball rebounds elastically off the inclined plane. Oh, so it's like inclination something alpha. Okay, there's a ball that's falling down. Smooth inclined plane. Oh wait, zero initial. So it is falling. Oh, so I think it's not falling; it's sliding. I think. Is it like that? So then, if it slides distance h, the ball rebounds elastically. Oh, so no, 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 it is falling. Right. So it falls distance h. I think over here its velocity should have been zero. I think. Then it falls distance h. It rebounds elastically. Right. Then it's just moving. Oh yeah. So this angle, whatever we know what this angle is, 90 minus alpha, is the same thing as this thing. So 90 minus alpha. Right. Yeah, it's not supposed to be 90 degree over here. It looks like that. It's supposed to be 2 alpha. Yes. Having fallen distance h from the okay, the ball rebounds elastically off the inclined plane. At what distance from the impact point will the ball rebound for the second time? Oh, okay. So just move it up a little bit, and actually just draw it slightly better. So maybe this looks like 45 degree. I don't want it to look like 45 degree. I want it to look slightly different. Let's say maybe steeper angle will be better. It's still 45 degrees. This is better. So now it will be like this. Right, this complete angle is 2 alpha, and it falls like this, and then it goes like that. And it, yeah. So what's this distance? I think that's what they mean. Wait, 31. What distance from the impact point? Of course, this range. Fine. Will the ball rebound for the second time? So we just need to figure out. Oh yeah, so it's not that bad. Right. So this is going with whatever velocity is going. It's h right there, so you can find out the energy. So it's mgh is equal to what am I writing? Mg is equal to half mv squared. It gets cancelled. V is equal to square root of 2gh. That's with what velocity will rebound as well. So just square root of 2gh over here, and this angle is just 90 minus alpha. So cosine of, not cosine, it should be sine of that thing, right? And that's just going to be alpha right there. And this thing is alpha. This thing is alpha. So this times cosine of alpha. That would be this thing. No, that's not what we want. We first of all need to find out what a time period is, right? So that's why the vertical one, which is, oh yeah, so vertical one is in fact cosine alpha. Sine alpha would be different. Yes, that makes sense. So square root of 2gh cosine alpha, that's this thing. So 2 times of that upon g, right? That is a time period. And in that time, what's this displacement? So that will be ut. So u is just 2 square root of, sorry, not 2. Why am I doing that? Square root of 2gh sine alpha, right? That times the time period, call this in capital T for now. That's half at square, or actually plus half at square in this case, because, right? And now it will be, oh, it should not be g, it should be g. What's this component? Just g cosine alpha. Hey, that's nice. Cancels. Perfect. Right? I mean, this is cosine alpha, of course. It has to be. And that's also, this is weird. The time period is the same for some reason, huh? How did this happen? No idea. But it did happen. Okay, whatever. Just keep on moving. So that happened. Then what? So this is the time period, which is basically just 2 square root of 2h upon g at this point. So now this thing times the initial, that's supposed to be 2hg, and then cosine of this angle, which is sine alpha. So sine alpha times this thing, and then the time period. So 2 square root of 2h upon g minus half gt, so plus half gt square, so half of, now no, sorry, not g, a in this direction, that is just g sine alpha upon t, so g sine alpha, right, and that times t square, so the square of this thing is just 2h upon g. Oh, there's also 4 over there, so that will just make it 2 right there. Yes, that's how it should be. So this cancels. This is 4h sine alpha, and this thing, this cancels, just have 2, and then okay, 2 times 2, 4 4h sine alpha over there as well. This is awesome. So we mean 8h sine alpha will be the thing. Is that what we mean? I think so. Just check this once again. It fell down with h, so half mv squared is equal to mgh. At least that's what we do. We will assume over here it was 0. That just gives us v is equal to square root of 2gh, right? Then we figure out what a time is, so just square root of 2gh times cosine of this angle, so square root of 2gh cosine alpha, and then that upon this downward acceleration, so that's g alpha, 2 times of that, of course. So from that we got the time period, which is basically square root of 2h upon g, 2 times of that, and then we just need ut plus half at square. So u is in this case the x component, which is square root of 2gh times sine alpha, so that's why this thing, all right, that times time, so this plus half a in that direction is just g sine alpha, right, t squared, so this thing squared, so for that 4 will be there, and then it's 2. Yes, nice, looks good. It should be just 2h into sine alpha into 2, so 4h sine alpha, and then this is also 4h sine alpha. So 8h sine alpha is the way to go. 31st done. Now this is the kind of question I wanted. 32. Okay. Right. A cannon and a target are 5.1 kilometer apart and located at the same level. Cannon and a target are 5.1 kilometer apart. Okay, and located at the same level. Cool. So how soon will the shell launched with the initial velocity something reach the target in the absence of air drag? Absence of air drag, fine. I don't get it. Wait. Same level, 5 kilometers apart. It's just shooting what angle? Okay, so the angle is such that it will hit it, right? That's what we assume. Fine. So basically your range is given. So the sooner the better, of course. So what we want is that the range, that is the one given to us. So that will be whatever initial velocity you put that with, and then sine of 2 alpha, where alpha is the angle that it makes with horizontal, that upon g. Yeah. So from there you can figure out what 2 alpha is, and what we actually want is the time period. So, time required, that will be time of flight, of course, 2u sine alpha upon g. So from this we want that, right? Okay, that's kind of a complicated question because, right, I mean from sine to alpha you want sine alpha, huh? This is almost the same as solving the quadratic. No, that's not nice. Okay, maybe we should write in a different format. Using ux and uy would be better, I think. So basically, you know what 2ux uy is, and what we need to figure out is just uy squared, 2uy squared upon g. So how would you do that? Wait, what's it is 32, right? So you just know what u square is. You don't even know what that thing is. So maybe this is the better way. Fine. So you know what this is. You know what that is. That is okay. Maybe this will give us some nice quantity. Let's do it. So what's the range? 5.1 kilometer. So basically 5100. Yeah, so 5100. That upon, so that times g, of course. So g is, let's just say it's 10 upon u square. So 240 squared, I think. Yes. So that's 100, of course, and that cancels with this, and then 24 squared. Oh, now how do I calculate that? 51 is like 17 times 3. Not helpful. 24, not working. Plus 34 would be really nice. But okay, you can cancel 3. Factors of 3 are good to cancel. You can maybe write this as 9.8 so that you can cancel some factors of 4. Okay, so maybe write this as 9.8. Okay. But still, it's not giving us anything that from which we can directly figure out what sine of 2 alpha should be. So it's just not good. It's just not good, right? Fine. 9.8. Let's just do it. So 24. This isn't giving us anything nice. Okay, this is going to be 17. This is going to be 8. Let's see. This is, so it's multiple of 4, I think. So 8 and no, it's just 2 multiples. So 4 right there, and this is going to be 4.5 and 4, so 4.9. Not helping, not helping. 17 into 49 upon 14 to 24. That's sine 2 alpha for you. Now, how do we go from here to sine alpha? I don't want to be solving a quadratic. You write it as 2 sine alpha cosine alpha, but then cosine alpha should be written as square root of 1 sine square. And then it just becomes really complicated. Is it even worth doing it? Or maybe I should just use, okay, sine inverse of this thing, half of that, and sine of that thing. But that's just stupid, right? That is just not nice. So you don't know what to do. Sine alpha won't work. Tan alpha, that's an easier quadratic to solve. Yes, but it's still just a quadratic and with very bad coefficients. It's just not good. It's not doable. Oh, come on. Are you serious? Why give us this kind of... There's no way I can calculate it by myself. I would need a calculator for this thing. So you know what? Scrap that. I'll just say sine inverse of this, whatever that is, we don't care. Half of that, right? And then sine of that, whatever that is. or in fact, even better, just say alpha is equal to half sine inverse of 17 into 49 upon 40 to 24. Because seriously, how would we calculate this kind of huge thing? Okay, once you have that, just put this thing in there and you are done. So time period is just 2 times of u. U is 24, so sorry, 240, and that times sine alpha. Sine alpha we don't know. Okay, that upon g. G is 9.8, right? I mean, I hope they don't take 10 into there. Whatever. So 4 multiple of 4 or multiple of 2. Okay, first of all, so 240 upon 4.5 and then 3, so 4.8. Wait a second, sorry, 4.9 for sine alpha. So 2400 upon 49, not really so anymore. That's it. That's what our time is. All right. So this is as far as we can go. Now what? We got that. What do you want us to do? Okay, that's all you wanted to figure out, huh? That's it. Next. But it feels bad giving us, giving them this kind of answer. We could try to do this. No, you shouldn't. Okay, first of all, let's just check if it's correct. I mean, okay, 17 upon 24, and uh, is this sine inverse value correct? Is this thing less than 1? I think so. 70 times 49. Approx, okay, it's like it's less than 18 times 50. 18 times 50 is 900, and this thing is 960. So yeah, it is less than 1. Fine. Let's go to the next question. 33. 33 is 32 is done. 30. Oh, and by the way, this is not the only value. You could also have pi minus this thing, but I'm gonna take the smaller value because I want the smallest time. So to 33. Cannon fires successively 2 shells with velocity this and okay, fine. First at an angle theta 60 degrees and second theta 45 degrees horizontal. The azimuth. What does an azimuth mean? I think probably it means like the height of this something. Yeah, because okay, what does azimuth actually mean? Is this the range or the height? Wait, let me add that. Okay, we don't know what is supposed to be happening. What is the azimuth? Is this a technical term? I've never seen this before. Okay, just question mark. No idea what this actually means. But okay, let's entertain the possibility. What could it be? Maybe it could be the height or it could be the range. So you gave us the angles, time interval between, okay, and both with the same velocity. Give us the angles. Giving the air drag. Oh, I think it means they want us to do it at simultaneously, right? Because everything is in fact fixed. You have V not fixed. You have theta 1, theta 2 fixed. There's only one thing that you can vary, that when these are launched, right? Nothing else that you can do. So that only means they are doing this simultaneously. Neglecting the air drag, find the time interval between firing. Wait, what? Okay, I just said it's supposed to be simultaneous and now they are saying time interval. Collision of shells. Okay, now this is suspicious. I don't know what this means. Next. A balloon starts rising from the surface of Earth. The ascension rate is constant and equal to V0 due to the wind. The balloon gathers the horizontal velocity component Vx is equal to Ay. Okay, wait, what? Ay. Y is the height of the ascent. Oh, all right. So, fine. Where A is a constant and Y is the height of the ascent. Okay, find how the following quantities depend on the height of the ascent. Oh, okay. So the ascension rate is constant, right? So you can say, okay, y is just v naught times time. And then vx is equal to a v naught t. So vx is also just, yeah, right. The horizontal drift of the balloon. So xt, it's related to the square of the time. So let's do this, right? We can do this. Okay. So we'll have Vx is equal to a v naught t, and thus x is equal to half a v naught t squared. But then guess what's t? Or even better, right? It's like this: a upon v naught and v naught t squared, which is just y squared. And there we go: a y squared upon 2v naught. That is the x. So the drift is a y squared upon 2v naught, whatever. Next question. So b. The curvature radius of as a function of x. Are you serious? Okay, so you know what the actual velocity is like, the vector, right? So you got vx in this direction, you got vy in that direction, or v naught in that direction, whatever. And you want the curvature radius. So v squared upon r is equal to the acceleration. Oh, okay. The perpendicular component of the acceleration from this velocity. First of all, let's write what velocity actually is. So it's just base comma v naught, and that will be v naught a t comma. So a is unitless constant, I think. Where is it? Where did it go? A, no, it's not. Right, okay, this has dimensions of 1 upon second. So this actually does work. So this and 1, something like that. And what's your A vector? Taking the derivative of these things, well, V naught times A comma 0. Cool. So hey, this is nice. Your acceleration is completely in the horizontal direction, right? And your V is somewhere in that direction, of course. So right, let's do this thing. So if this thing is making angle alpha, right, then you just have tan alpha is equal to 1 upon 80, right? And this is your acceleration. Oh, it's supposed to be in horizontal direction. So this is in horizontal direction completely. This is 90 minus alpha. So a cosine of that, a sine alpha, that's what we are looking for. A sine alpha is this thing. So yeah, v squared, which is just basically this plus that squared. Okay, so it's supposed to be v naught squared into a squared t squared plus 1, that thing, upon a. So that is just a sine alpha. Yeah, exactly. Oh, sorry, v naught a sine alpha. Pause. Yeah, v naught a sine alpha. That should be 1 upon, sorry, no, equal to r. That would be v naught upon, wow, this is weird. Is this how it's, I mean, like, a is unitless. No, it is not. It's not unitless. Right, this makes sense. A sine alpha, a square t square plus 1. Now, sine alpha, what is that? Sine alpha, well, you know what this thing, okay, fine. This is supposed to be this thing, so 180 and square root of a square t square plus 1. So 1 upon square root of all that stuff. So divided by that thing, r is supposed to be equal to v naught a square t square plus 1 to the power of 3 upon 2 upon a. There we go. That's our radius of curvature instantaneously. And you want what? The curvature radius trajectory as a function of x. Are you serious? Why? As a function of x, you say. So you got what x is. X is half a v naught t square. So you just have to put t squared as 2x upon a v naught, and that should, oh no, charging low. So wait a second. By the way, this particular video is not actually supposed to happen right now because I was not going to do it, but I thought, oh, just do it. Right, back. Oh no, please don't do this. Okay, it is charging. Fine. Yeah. So where are we? You got what r is, and you want in terms of x. So t square is this thing. Just put that in it. R is equal to v naught a square times this. So 2ax upon v naught plus 1 power 3 power 1 upon a. Now write it in a better way. So r is v naught upon a into, where did it go, 2ax upon v naught plus 1 to the power of 3 upon 2. That's kind of nice. Actually, you don't realize this, but we are actually creating general formulae everywhere. So maybe if I overlook this, I will have many more simple formulae that rather than doing the whole derivation again. But yeah, remembering all of that, whoever does that. Okay, 35th. Right, this was 34th. Right. Oh no, I mixed up something. They wanted the total tangential and normal acceleration of the balloon. They didn't want the curvature radius. That's from 35th. That's not 34. Okay, it's messed up. Uh-oh. Yeah, well, just extra information. Just put this as extra information. So let's do B now. What do they want? Total tangential and normal acceleration of the, oh, so the normal acceleration actually we did found out, right? Yeah. What was it once again? It was sine alpha times a, right? Exactly. A was the acceleration. Sorry, av naught in the x direction, right? Oh, come on, just draw it once again. Can't believe this is happening. Okay, so your x, what was that? We don't actually care. What is Vx? Where did it go once again? X is equal to Ay. So Vx, so V vector is just equal to Ay, which is Av naught t, comma V naught t. Sorry, just V naught, not t over this. It's just V naught a t comma 1, and that's how A vector was just V naught and a comma 0. Right, and we just want the normal and tangential acceleration of the balloon. Wait, normal to what? Normal, I think they mean normal to V. Fine. So then, once again, the same thing. You just got alpha over here, and it's like 90 minus alpha or whatever. This thing would be A vector. This is 90 minus alpha, and that's why A vector sine alpha was the thing. So that would just be V naught. So our A normal is V naught A times sine alpha, which is 1 upon square root of a square t square plus 1, right? So that's something we know. A normal is equal to this whole thing, av naught upon square root of a square t square plus 1. All right, what about the tangential acceleration? So a tangential is av naught times a t naught, sorry, a t, so a squared v naught t upon square root of a square t square plus 1, because of course cosine, that all of this just belongs to this, right? And the total acceleration, come on, total acceleration is pretty easy. It's just this. So a total, how do we put that? I don't know. So magnitude of a vector, that is just v naught a. Nice, right? Cool. Next question. 35th. 35th is a particle moves in the xy plane with a velocity v vector is equal to ai plus b. So what's the velocity? A plus, sorry, okay, a and b x. Wait, what? That's x over there, not, huh? A, b are constants. At the initial moment of time, the particle was located at point x is equal to y equal to 0. Fine. Oh, so it's that kind of question. Of course, we already did something like that previously, right? Perfect. So now we know how to do it. Dx upon dt is equal to a. I think a and b are constants, right? And then dy upon dt is just b times x. Now what? Divide these two equations. So dy upon dx, that is just bx upon a. Wow. There we go. Ay is equal to bx squared upon 2, and then plus some kind of constant. What constant? Do we know what its initial position is? Oh, it's located at x equal to y equal to 6. So that's c0. Gone. So that's nice. Bx squared is equal to 2ay. That is the locus of this thing. The equation of the particle's trajectory. Done. We got it. So you can just write y is equal to bx squared upon 2a. That's part A, right? This is a nice question. Good thing we did that kind of super hard question before. So now we can do this easily. And next, what you want? The curvature radius of trajectory as a function of x. Curvature radius of radius. So you need acceleration as well. Oh wait, but isn't the radius of curvature completely dependent on the geometry and not actually on? Oh yeah, it's a function of x. You say it's kind of like a parabola. So a circle that touches the parabola and also hugs it the closest. Okay, maybe it's better to just go with v squared upon a. Right? Yeah, you could just do that. I mean, you already got V. Now just need A. And how would you figure out A? By using a time dependence. So you can just plug this thing in this formula, right? Yeah, so V is this, so Y is this thing. So dy upon dt, that's just going to be equal to d upon A times x dx upon dt. Plugging that into here, we just get, well, d upon A dx upon times x dx upon dt is equal to b times x. Nice, cancels. So dx upon, oh, so this wasn't actually that hard because you already gave us an equation independent of y. Why? Now I feel dumb. Fine, so x was just a times of t. Nice. From it, everything is just doable. So y was, now you already have it, so y one differential. Okay, so p times x squared and upon 2a. That will be ab upon 2 times t squared. Cool. So these are our two useful relations, right? And now we can figure out what our v vector should be and what our, well, v vector already we know, right? What our a vector should be. So our a vector is, of course, the derivative of v vector, which is 0, and then v dx upon dt. And guess what's dx upon dt? It's just a. Exactly. So that will be ab. Nice. It's completely on the y-axis. And now we just need to figure out its normal component with this thing. Honestly, I don't like that. Okay. So Vx, you know, right? Sorry, V, you know, is just a comma Bx. And this thing is just going up. AB. So acceleration. What's this angle going to be? In fact, maybe I should ask what this angle is going to be, because that's what we'll need. Once in theta. So just have, okay, yeah, this triangle is enough. And we just need to figure out what AB cosine theta is. So this will just be V squared upon AB cosine theta. And what's V squared, by the way? It is just A squared plus B squared x squared upon AB cosine theta. And cosine theta is just A upon all that stuff. So AB times A upon square root of A squared plus B squared x squared. So this will just be equal to a squared plus b squared x squared to the power of 3 upon 2 upon a squared b, basically. Now I have to put that in. So b, that is the second thing. So radius of curvature, that is this quantity. Simplified somehow? No. A squared b, that's it. Next. 36th. I really wished it was doable by our method, but actually it's doable by simpler methods. Okay, a particle A moves in one direction along the given trajectory with tangential acceleration is this, okay. A is constant vector coinciding in direction with x-axis. Oh, okay. And tau is a unit vector coinciding in, oh, so it's like a dot product of this, I think, yeah. Tau is a unit vector coinciding in the direction with the velocity vector. Oh, okay. At a given point. Wow. Find how the velocity of the particle depends on x, provided its velocity is negligible at the point x equal to 0. So first of all, okay, it's tangential acceleration as a number, I mean as a quantity, not as a vector. Yeah, so tangential acceleration, wait, what? In one direction, wait. You just said it's moving in one direction along a given trajectory. Wait, I don't get it. Along a given trajectory. No, something's wrong about this. But you just said it's along one direction, so then how does this even make sense? Tangential acceleration. It's just acceleration. Is this supposed to confuse us, or is this actually telling us anything? Oh, figure 1.4. Ah, nice. Oh, so it does move along a non-linear path. Why did they say it moves along one direction? I don't know. Huh. So, yeah. Right. So now, how do we solve this? Where A is the constant vector coinciding direction with the x-axis and T is the so the tennis is that. Huh? Mhm. Wait a second. Talk about the total acceleration first. The total acceleration, if you know that, how would you figure out what tangential acceleration is? It would just be the A vector, whatever that total acceleration is, dot B vector upon the, I mean, it should actually be A hat, right? So A vector upon magnitude of A, and that, oh, sorry. It should be A vector dot V hat. Yes, so V vector and then the magnitude of this thing. That would be your tangential acceleration. So that should be equal to omega t. And that they just told us is this thing, A tau, so A dot tau. So A is a constant vector coinciding with the direction of the x-axis. Okay. And tau is a unit vector coinciding direction to velocity. Oh, so you can just say this thing was tau itself. So A vector dot tau was, oh, I should probably say this thing. Okay, so don't use that. Just use W. W vector. And I don't like using W. It just feels awkward. So this tangential something. Okay, cool. Is equal to this or that. Okay, this is not enough to conclude that W and A should be the same. So W is A vector plus something normal to the trajectory, right? Okay, but hey, at least now you know that what the x what is the that kind of component. Okay, this is not useful. Something normal to that, huh? Oh yeah, sorry. What was that? W is equal to A vector, which is along the x-axis, and that plus something that is normal to this thing. Exactly. So, oh, okay. Wait. This is actually nice. Something that's normal to this. Okay. And how is this gonna be useful? Velocity vector at given point. Find how the velocity of the particle depends on x, provided its velocity is negligible at point x equal to 0. Velocity of the particle depends on x, you say. Ah, oh, come on. Don't be like this. Oh, it's not helping. And also we say that W is the total acceleration vector. Yes. WT with the that thing, of course. Come on, think. Gotta think a bit. Wait, how do I mean, if this acceleration can change, how do I figure out what this should be? Oh no. Changing the acceleration completely changes the trajectory itself. So, how can I figure out anything from it? So, how it depends on x, just x. But you are saying it moves like this. So, yeah, why would it just depend on x? It should also depend on y and stuff, but it's not doing that. Wait, if it's just 2D, we can just plot this as x comma y, and then, okay, fine. Some normal along that, say. Okay, cool. think calm-headedly. Dots the same. That's all we know. Right. It's the one perpendicular to that, huh? So your v vector is tangential to this thing. So let's just call this dy upon dx. So dy upon dx is the slope of that, right? Call this thing as tan of theta. Okay, you know what? Let's do it using theta then. At this point, the trajectory is at theta with x-axis. Then what you're saying is that it's just some acceleration over here, which is of course a vector, and then some other acceleration called b vector maybe in this direction. That's what the actual acceleration is, right? Oh, cool. And the velocity, it always points like this. Why is this so complicated? Wait a second, the velocity points like that. So you got what, how x changes, how y changes, right? If you know what the velocity is, of course. And how does the velocity change? That will be the vector sum of these. Yes. You will have to assume this b vector to be variable, otherwise it's not solvable, right? So let's do it. Just do it. Okay, so that's a vector along that. So for x, you will just have a plus the magnitude of a, that is plus, so this guy's component is this is just 90 minus theta, so cosine of that, sine theta, so b sine theta in this direction, right? Yes, and that is equal to a x component of the velocity, sorry, not the x component of the velocity, but acceleration, in fact. Yeah, and the y component of the acceleration, that is just this thing. So that's, oh, so just it's just dependent on b. It's b. It is not dependent on anything else. So b sine of this is like cosine of theta, right? Negative of that, of course. That is a y. And what do you know? You know that. Wait, what? Oh, that's weird. Okay, don't think about it too much. So that is dvx upon dt. Yes, that's doable. You can also write this as x dvx upon dx. Yeah, that's one thing that you can do. And this thing can be written as, similarly, this thing can be written as wow, I really want to write this in time. So d square x upon dt square. That would be one thing that we can do, but I'm afraid that won't work. Okay, and then this is y dvy upon dy, this thing. And what do you know? You know that dy upon dx, that is just equal to tan theta. Are you thinking what I'm thinking? Yeah, we should just figure out what dy upon dx is from using this thing. Of course, I mean that would have worked if this was not. Oh, come on, it's not velocity. It's acceleration that we're dealing with. That makes it so much worse to solve. Okay, think. So how does the velocity vector change with x? That's what we are asking. Come on, man, think about it. Okay, think. You can use that, or then no, it's not gonna do it. So you can say, okay, x dvx upon dx minus a upon y dvy upon dy, that should be equal to negative tan theta, which is negative dy upon dx. That's one thing that we can do, but how is this even helpful? No, it's not. It's not helpful. When this was the first order differential equation, it was good, it was solvable, and now suddenly it's not because it's second order. Once again, what we need to find how the velocity of the particle depends on x, while its velocity is at point x, 0, whatever. Once again, that's acceleration. It's not what. Okay, you have to use Cartesian coordinates for this because this thing is along the x-axis, so that will be the easiest to do. I don't know. And yeah, I think it is one of those questions which is just not solvable directly. Instead, I'll have to give it some time. Why is this so hard? Okay, fine. Let's see you guys in the next video.